Welcome to the video for Lecture 14, Section 2. This video continues the discussion about actuators. In this video, we will talk about key characteristics of relays. Here is a list of actuators, and there are all devices that are commonly used to manipulate a process input. You will see some of these actuators in some of the labs. For our purposes, relays are described as electronically controlled switches, and light switches are used to turn lights on and off. Some light switches are dimmer switches that can dim the lights rather than turn them totally on or totally off. The switches and relays we are talking about now are two-position switches that turn a device such as lights and pumps on or off. Now, when we say that the relays are electronically controlled switches, we mean that the relay's action depends on the control signal that it gets from the controller. Remember that the actuators get an input signal from the controller, and that controller signal tells the relay to either turn on the power or turn off the power. And for our purposes, we are dealing with relays that turn the device that they are attached to either on or off. Relays have two circuits attached to them. One circuit is called the load or contact circuit. This circuit is connected to the device that the relay is turning on or off. The other circuit is the control or energizing circuit. This is the circuit that is connected to the controller. In the lab, you will see relays connected to the digital input and output side of the PDAC55. The connections made to the PDAC55 will be connected to the energizing or control side of the relay. The load side will be connected to a fan or light bulb. The control side usually has much lower voltage, so it is considered the low power side of the relay, while the load side is considered the high power side of the relay. The relay shown here is a solid-state relay. Solid-state relays do not have moving parts. This slide shows some electromechanical relays. The term electromechanical means that there are moving parts that are moved to the application of an energizing circuit. Electromechanical relays have a coil with a permeable ion circuit that, when energized, moves an armature that opens and closes a circuit. When the circuit is closed, the armature moves to close the circuit. The two sides physically touch, so the resistance to electrical energy flow is very low. When the circuit is opened, the armature moves to create a gap in the circuit is open and electrical power cannot flow. The resistance to flow is very high. These electromechanical relays are used for high power applications like 10 horsepower motors. The low resistance when closed and the high resistance when open are big advantages of electromechanical relays. However, one of the disadvantages of electromechanical relays is that they have moving parts that can wear out over time. Electromechanical relays can open and close in the range of 100,000 to 1 million times. This slide shows a solid-state relay. They are very common. Internally, Solid-state relays use semiconductors to turn power on and off on the load side of the relay. We will not get into the internal workings of solid-state relays. Compared to the electromechanical relays, solid-state relays are used for lower power applications. It is common that solid-state relays cannot have more than 15 amperes on the load side. So, a solid-state relay that can handle 240 volts and up to 15 amperes can control 3.6 kilowatts of power, which is around 4.8 horsepower. Solid-state relays have very low power input requirements. You will be able to control them with the PDAC-55 in lab. They are also faster than electromechanical relays. Without moving parts, they can last longer if they don't get overloaded. One disadvantage of solid-state relays is that some may have what is called a leakage current. A leakage current is the current flow that continues pass through on the load side of the circuit, even though the control side of the circuit says to open the circuit. Leakage current is inherent in semiconductors. Leakage current may not be a problem with some loads, but if leakage currents are a problem, they can be managed with opto-isolators. There are thousands of relays available for purchase, so I want to spend some time going over some of the criteria or specifications that engineers need to consider when selecting a relay. Here is our list of relay selection criteria. Some of these criteria are unique to relays, and some are criteria that apply to many actuators. Let's go over some of the criteria listed. The first relay specification that I will talk about is the number of poles. With relays, the number of poles describes the number of circuits switched with a single relay. One way to think about the number of circuits is think about the number of lights or number of electric motors that a single switch can turn on or off. For example, one of the light switches in the classroom turns on several lights. All of those lights are on one circuit and they are controlled with one light switch. A single pole relay controls one circuit, so it just have one switch that turns on or off all of the lights on that single circuit. A double pole relay controls two circuits, so it would be able to turn on or off two sets or two circuits of lights. Three-pole relays can control three circuits, and I bet you can guess that a four-pole relay can control four circuits. They are commonly abbreviated using SP for single pole, DP for double pole, and 3P for three-pole relays. The picture shows a double pole electromechanical relay. The next relay characteristic is the number of throws. Relays and switches can sometimes be built in different ways so that they can be used to manage two circuits. The term throws describes the number of contacts of connections that a relay or a switch can make. The little diagrams on the right side of this slide try to illustrate the concept. The top figure is a single throw. It can only make one connection when the armature on the left drops down to touch the arrow and close the circuit. The double throw circuit starts off connected to the bottom circuit. If the armature to the left is moved up, it disconnects to the bottom arrow and connects with the top arrow. So this switch can make two connections, so it has two throws. A double throw switch is used when you want at least one of the two circuits active. Let's say you want either one to work. The double throw center of switch has another option. The armature to the left can stay between the top and bottom circuit on the right. So neither circuit is connected. Hence, the name double throw because it can make two connections, but it can make no connection, and this is called center off. So throw describes the number of contacts or connections that the relays or a switch can make. Another characteristic of a relay and many other electronic devices is called the normal position. The normal position tells us the relay or a valve position in the de-energized state. The two little sketches illustrate the two options. The top sketch with the gap between the armature on the left and the arrow connected to the circuit on the right is the normally open circuit. It means that when the relay is not energized, the load circuit is open. The bottom sketch shows the circuit connected. This indicates that this relay will be connected when the relay is not energized. Next, let's talk about make and break. This characteristic describes what happens after the relay is energized. The top little sketch shows a single-pole, single-throw relay that is normally open. The normally open characteristic means that when the relay is de-energized, the circuit is open. When the relay is energized, the relay will close or make the circuit. The middle little sketch shows a single-pole, single-throw, normally closed circuit. The normally closed characteristic means that when the relay is de-energized, the circuit is closed. When the relay is energized, the relay will open or break the circuit. The bottom sketch is a single-pole double throw, so the top circuit is closed in the de-energized state and the bottom circuit is open in the de-energized state. When the relay is energized, the top circuit will open or break, and the bottom circuit will close or make. When ordering relays, the common sequence for listing these four characteristics is as listed here. First, it's the number of poles, followed by throws, followed by normal de-energized position, and then any make or break characteristics needed. So the first example is a single pole, single throw, normally open relay that will make a circuit when energized. SPST NOM. The second example is a three-pole double throw normally closed relay that will break and make circuits when energized. So 3PDT NCBM. As you look for actuators, you need to also notice the energizing or control circuit rating. This describes the minimum amount of power needed to energize a circuit. This means that the control circuit needs to supply at least the minimum control signal power to energize the circuit. If the control circuit does not supply that much power, the relay won't energize and change the relay. Another limit on the energizing circuit is the maximum amount of power that is allowed. Applying excess power can burn out the relay. The next characteristics that we talk here is that you should be thinking about when selecting relays and other devices with coils is the duty cycle. The duty cycle describes the maximum amount of time that the device can be energized before the device begins to generate excess heat. If a device that has 100% duty cycle, that means that the device can be energized continuously or 100% of the time. If the device has a duty cycle less than 100, it means that the device needs to be de-energized part of the time. So a device that had a duty cycle of, say, 50% is a device that needs to be de-energized at least half the time to prevent overheating. The duty cycle is calculated using the equation shown here. It is 100 times the time on over the time on plus the time off. So if the device is energized, say 4 minutes out of every 10 minutes, the on time is 4 and the off time is 6. The duty cycle, therefore, is 40%. Some more characteristics of electromechanical devices with coils are the coil power requirements. These describe how much voltage and current or power is needed to energize the coil. One would expect that larger coils on large magnetic relays will probably need more power to energize them. Response time describes how much time it takes for the relay to actually respond once the control signal is sent to engage. Again, with electromechanical relays, large ones may have a substantial delay between when the control signal says engage and when the relay actually engages. Similarly, there may be a delay between when the control signals say to disengage and when the coil and relay actually are disengaged or drop out. So pickup time describes the delay when engaging an electromechanical relay, and dropout time describes the delay when disengaging the relay. In many situations, the delay is not important, but in some situations, things are timed very carefully, so an excessive delay in pickup time or dropout time could be an issue. For the previous slide, we talked about unwanted delay. In some cases, you might want a delay either at the beginning when engaging some device or at the end when disengaging the device. So there are relays and other devices that have a time delay built into them on the pickup or the dropout. The top sketch shows a delay between when the energized signal says turn on and when the contact or load circuit energized. The bottom sketch shows a delay in the off signal. The final characteristic we talk about is the load circuit rating. This tells you the type and maximum electrical load that the relay can handle. Some relays can only control alternating current devices and can only control direct current powered devices. Some can only control direct current powered devices. The load side will usually either give the maximum kilovolts or horsepower that can be controlled by the relay. Finally, if you use electromechanical relays, the materials used that make or connect the circuit need to be good materials, will low electrical resistance, and avoid arcing when they are disengaged. The materials should also not pit or erode when they open and close. This brings to the end of the lecture 14 section 2 video. The next video will cover solenoids. Please write down any questions you have and bring them up in class or lab. Thank you.